Hello everybody, I'm going to talk through today all the worked solutions for paper 2 on higher tier from the November 2023 research series for Edexcel's maths. So I'm going to get straight into it, talk through all the questions in order, as of course you'd expect, and for some questions I'll show more than one way of thinking through the answer to try and help understanding. As ever, if a video comes up short or you feel I'm not explaining it in a way which you can grasp, do please put a comment on the comment section, email me if I teach you, or try and see me in and around school. So do let me know if this video doesn't answer all your questions. I'm sure it won't, but I am quite confident it should help to a good extent. So without further ado, let's just get stuck in. Let's talk through together question number 1. So question 1 is purely algebra. So the first one is just expanding and simplifying. So I'm going to write these brackets out again myself, just bigger and clearer to illustrate the solution. So we've got 3 lots of 2y minus 5 plus 7 lots of y plus 2. So expand means get rid of brackets. So the first step, expanding these out, 3 times 2y will give 6y, 3 times minus 5 will be minus 15. So this bracket becomes 6y minus 15. I'll show you the green one as well. For green, 7 times y is 7y, then 7 expanded with the positive 2 gives positive 14. Now we need to simplify it, so we're going to group together like terms. I'm going to give you a strategy now for if you're not sure or get confused about how to group terms together. Sometimes the signs confuses people. So my little tip is, if you don't like the signs or the signs and symbols are a source of confusion, put lines before signs. Lines before signs. So what do I mean? Here's what I mean. Put vertical lines in before any symbol. This separates out if the minus relates to the 15 or the 6y. The symbol always relates to the thing immediately after it, but putting vertical lines in separates it out quite nicely until you gain the confidence where you don't need to do this anymore. So let's have a look at the y's. I've got 6y here and 7y also. So 6 and 7y in total is 13y. Next, looking at the pure numbers on their own, I've got a minus 15 and a positive 14. So dealing with these, overall, 14 take away 15, overall will be negative 1. So the numerical part of the solution is just minus 1. Therefore, the final answer is 13y minus 1. We can now have a think about part B, where we're factorising fully. Now, factorising means create a bracket, or sometimes brackets, for example, if it's a quadratic. This one here, all the terms relate to x's, x squared, and then just normal x's, if you like. If it's a quadratic where it's just x squareds and x's, or y squareds and y's, this will always factorise, if it factorises at all, that is, into a single bracket. So first of all, let's have a look at the numbers. I've got 6 lots of x squared, 15 lots of x. Factorise, the clue is in the name, I need to find the biggest number or biggest thing that fits into 6 and 15. What's the highest common factor of 6 and 15? That's 3. So outside of brackets, I write 3. Next, I look at the letters, x squared and x, and then consider what's the largest number of x's in each of these x terms. Well, x is just one lot of x squared is x multiplied by another x. So 2 lots of x here, multiplied, only 1 lot there on its own. So all I can say is common in each is just 1x. So I write 1x as well outside the brackets. So I have a 3 and an x outside. Is it anything else common to each of these 2 terms? No, there isn't. So once I've factorised out everything I can, which I have, I then add in my brackets like so. Next, I've got 3x. I want to have 6x squared. To go from 3 to 6, I need to multiply by 2, so I put a 2 in the bracket. To go from x to an x squared I need to multiply by x by an extra x, so that becomes 2x. Plus in between, so stick a plus sign there. Finally, to go from 3 up to 15, I need to multiply by 5, hence my final thing in this bracket is a 5. I don't include any other x's, because if I did, I'd get x times some more x's, which give me at least an x squared, which I don't need. So that's the only thing I need to do. That, therefore, is my final answer. Part C, I need to make g the subject of this formula. There are a few ways of doing this. The final thing I'm going to say before I run into this one method I'm going to show is to make something the subject of a formula. All that means is write that thing on its own before the equals sign. So my target is to rearrange this to something that looks like g equals and then the appropriate expression. What we can do here, because it's a linear equation, no squares or cubes or square roots, and it's just talking about 3g, I can start with g on its own, and then consider what's happening to g with each step. Well, the first thing that g encounters is this 3, so g gets multiplied by 3 first of all. After being multiplied by 3, we add 11. That gives us 3g plus 11, and that of course is equal to f. And so the end result of that is it equals f. We can now reverse each and every step to get back to what g was in the first place. So if we start from this end with f and go the opposite way, and because we're going the opposite way, we're going to do the opposite things each time. So we start with f, now we're going to subtract 11 because we're going back, so we have f minus 11. The next step, instead of multiplying by 3, we'll do the opposite and divide by 3, and that gives us g. So therefore, what we've done to get g is we've taken f, we took 11 away, and then we divided that whole thing by 3. So therefore, g is f minus 11 all over 3. So we write that, of course, using mathematical language and put the equals sign. In other words, put simply, g equals f minus 11 all over 3. Question 2, we have a question which relates to percentage profit, which Karen is going to make for this charity. So before I even get into the information in the question, I'm going to focus on this thing, percentage profit. Well, percentages, if we remember, are very much like fractions. So I'd consider this as a fractional profit, and then once I've got a fraction, we can then just multiply by 100 to change that fraction into a percentage. So all profit really means is it's the difference in between money taken in, usually from sales, subtract minus money a person has to spend, for example, on costs. So the percentage profit, once we know what profit is, will be the profit as a fraction of the total money she's spent, and then we take that and multiply it by 100. So I'm just going to put this in the corner. It's profit over money spent multiplied by 100. And just to remind what profit actually is itself, profit in green, profit you can think of as money she takes in her case because it's Karen, minus the money she spent in order to make that money at all. So we can now focus on this information. So in the question, money spent is all of this here, 100 quid on food, 120 on a haul, £80 on a DJ. And the money she takes in from the tickets is £7.50, but 54 times. So if I total all this up, then she spends £300, but the money she takes in from the ticket sales, because it's a calculator paper, why not use the calculator? So 54 tickets, £7.50 each, that's going to be 54 multiplied by £7.50. Just get the screen so you can see it nice, big and clear. So 54 times £7.50. That gives us a total of £405 she makes from the sales. Therefore, 405 is the money she takes in. So the profit is just a difference in between these two totals. In other words, overall, she makes a net profit of £105 because she ends up taking in £105 more than what she spent in the first place. So now we can just plug these figures into this formula. So the profit is £105, but the money spent, I'm going to highlight in red, because it's here, was 300. So money spent is 300, and the profit on the top of the fraction is 105. Therefore, the percentage profit will be 105 over 300 multiplied by 100. In other words, percentage profit is going to be given by this formula. So let's work it out together. So on the calculator, 105 over the 300 she spent multiplied by 100 gives us a percentage profit for Karen of 35. So therefore, the final answer we need is 35%. Question 3 begins with Andrew investing £4,500 in a savings account for 2 years. The account pays compound interest at a rate of 3.4% per year. Calculate how much he has in the account at the end of the 2 years. So the key thing here is it's a percentage question, and in particular, it's regarding compound interest. So compound interest means we're going to add on to the starting percentage of what the amount is. And you need to remember, before anything happens to an amount, it always starts off as being 100% of its original self. Interest is where we add the percentage. So if the interest rate is 3.4%, we're going to start by thinking what 100% plus 3.4% is. So on a calculator, or just written down, this isn't exactly too hard. The overall percentage is 103.4%. So each time this percentage is applied, the amount becomes 103.4% of its original self. But more useful than that is to actually find out what 103.4% would be as a decimal. And to do that, we just divide by 100 and we get 1.034. This is the decimal equivalent of this. And this is a special number. This is called the decimal multiplier. And it's called that because we're going to be multiplying the starting amount by this decimal multiplier for each period this percentage change is applied. So what is the starting amount? Well, he starts off with £4,500. He gets this rate every year. So how many years is he getting this percentage change applied? Well, it says 2 years. So we're going to do 4,500 multiplied by this decimal multiplier twice. So we're going to multiply by 1.034 and then multiply by 1.034 again. But to put it simply, we're going to do 4,500 multiplied by 1.034 squared. Squared because it's 2 years. So type this on your calculator. You should find you get £4,811, and this doesn't quite make sense. So round it to the nearest penny, because we are talking about money. It then becomes, to the nearest penny, £4,811.20. And that's question 3 complete. Question 4, we have to solve this equation. 5x minus 14 equals 52 minus x. I'm just going to take the equation and write it bigger and clearer. So 5x minus 14 equals 52 minus x. To solve it, we need to work out what x is equal to. So the first move I'd suggest is to get all the x's together on the same side of the equation. It's normally easier to deal with positive numbers. So the best thing I would suggest to do would be to add 1x to both sides, because minus x is undone by adding x. So if I add x to the right, we'll have no x's left, and we need to add an x over here to make it balance. So like I say, if we add x to both sides, 5x plus x, this will become 6x minus 14, and on the right, minus x plus x cancels, leaving us with just 52. Now on the right, we could do with just having the numbers on their own. So how can I get rid of this minus 14? Well, the opposite of taking away 14 would be to add 14. So if we apply that step to both sides, adding 14, we'll now get 6x's equals 66. I don't want what 6x's are worth, I want just 1x. So to scale down from 6x's to just 1x, I can divide by 6. So dividing both sides by 6, x must be 66 divided by 6. In other words, x equals 11. For question 5, we have a ratio sharing problem. So we've got Chris, Debbie and Errol sharing some money in the ratio 3 to 4 to 2. And we're told here Debbie gets £120 of that. But then something changes. So that's the initial setup. Afterwards, Chris then gives some of his share to Debbie and some of it to Errol. The money that Chris, Debbie and Errol each have is now in the ratio 2 to 5 to 3. So the ratio's changed after Chris has given away kindly some of his money to Debbie and Errol. The question is, how much money did Chris give to Errol? So like I've stated now, this question's perhaps thought of in 2 different parts. Part A, before Chris gives Errol any money, and the second part is after Chris gives Errol some money. So considering this in 2 separate parts, what we've got here is this is before the money was shared, I've underlined in blue, and after money's been shared by Chris to Errol and Debbie, I've highlighted here in green. So let's think about before the money was shared. And usually with ratios, I'd suggest to do ratios using a table. So something like this would be my suggestion. So before anything gets shared from Chris to the others, think of it as a ratio of C to D to E. Chris, Debbie, Errol, and a total end column as well. So we're told before anything happens, the money they have is in the ratio 3 to 4 to 2. 3 plus 4 plus 2 is a total of 9 parts. However, we are told that Debbie gets £120. So Debbie's 4 shares, or 4 lots, or 4 portions, whatever word or way you want to think of it, must be worth £120. So 4 lots is £120. What must each piece be worth? Well, we could do 120 divided by 4, which is 30. Alternatively, and in the same way essentially, what number would we need to multiply 4 by to get it to 120? Of course, it needs to be 30. But to keep everything in the same proportion, if we're multiplying one of these ratio shares by 30, we need to do the same to the others as well. So multiplying every number in every column by the same total, we get that Chris must have had £90, 3 times 30, Errol, 2 times 30, 60, and the grand total amount of money between them, 9 multiplied by 30, is 270. We can now think about what's changed after Chris gives some of his money away. So if I construct another table for after Chris shares some of his money, we can now think of the ratio C, D, and E and how it's changed. The ratio has now become 2 to 5 to 3. 2 plus 5 is 7, plus 3 is 10. So there's a total of 10 parts now that are being shared. But from before, we were able to work out the total amount of money being shared was £270. So these 10 lots of money must be worth £270. So what have I scaled up by? What's 10 been multiplied by, essentially, to go from 10 to 270? 270 divided by 10 means it must have been multiplied by 27. So we multiply the values in the C, D, and D columns by 27 as well, and we arrive at the following. 2 times 27 is 54, 5 times 27 is 135, and 3 multiplied by 27 is 81. However, the only person we're really focusing in on is just Errol, and in particular what Chris gave to Errol. So if we just focus on Errol's amounts, from what he began with to what he's ended up with, he started with 60, but he's ended up with £81. Nobody else has given Errol any money. The question doesn't say Debbie's given him any money, it's just simply Chris giving him the money. So any increase in money Errol has obtained must be down to Chris. So if Errol's gone from £60 to £81, like so, then obviously his money's increased by £21. Therefore, it must have been the case that Chris gave Errol £21. Question 6, we're told the bearing of B from A is 147 degrees. Work out the bearing of port A from port B. If you notice here, the question, we're talking still about port A and port B, but now the order of where we're taking the bearing from is just switched. So if we're told from B to A, and we need to know the bearing of A to B, same places but just switched around, there's a really useful law of bearings which I'm going to show you now. In case you forget this law, I'll show you the standard way of doing it, which takes a bit longer, but which is probably safer. But essentially, the bearing law I'm talking about is this, and these are called back bearings. The bearing of B from A, if you know it, will always be 180 degrees more or 180 degrees less, basically 180 degrees different than the bearing of A to B. So if you have a bearing here which is less than 180, you can just add 180 degrees to it to get the bearing of, in this case, from A to B. If this figure was more than 180, for example 200, bearings are no more than 360 degrees. So if this were 200 degrees and we wanted the bearing of A to B, we'd have to do 200 minus 180, which would be 20 degrees. So why do we do 180 degrees more or less? Well, I'm going to give you a little visual to hopefully aid in understanding. So if I just write out A and B, obviously going to B from port A, imagine it as a straight line. Now, if I want to go from B to A, essentially, you can think of it as, I've gone on this direction, and to change direction, I need to change this direction by 180 degrees. I need to do half a turn to face back to A. And half a turn, of course, in terms of degrees, half a turn or half a circle is 180. So you can imagine yourself going from A to B and doing a half turn the other way to face back and return to your initial place. So using this idea, the bearing is 140 plus 180, which is 327 degrees. Using a standard diagram, which is a more traditional approach, we can start off like this. The bearing of B from A is 147. We're starting from A, so we do a north line pointing up from A and measure clockwise from north until we get to the line which is facing to B. So start at north, turn until we get to there when we're facing B. And as you can see, that's 147 degrees, just like the question said. We can now use some angle facts. Because these lines pointing north are both parallel, we can use the fact that co-interior angles add up to 180 degrees. So if this angle here is 147, this one plus this one need to add up to 180. So this angle at B will be 180 minus 147, which is 33 degrees. But the bearing of port A from port B is going to be starting from this north line at B, starting from B literally, all the way around until I'm again facing back to A. So that's the angle here, this reflex one, that's one I need to work out. So to do that, simply just do 360 subtract 33. So this angle here, the bearing of A from B, will be 360 subtract 33, which again, of course, is 327 degrees. So you can do that either way around. So question 7 is a question about a cylinder. So you can almost guess it's going to be about volume or surface area. But it's saying here, but it's got an empty tank in the shape of a cylinder as shown. The cylinder has radius 15 centimeters and height 43 centimeters. Now, the fact it says water is flowing into the tank at a rate of 0.47 litres per minute is a giveaway. They were interested in capacity, how much the container actually holds. And another word for capacity essentially is volume. This is a cylinder, so what is the formula for the volume of a cylinder? Well, we need to remember, because a cylinder is a type of prism, it's just the area of like the end shape multiplied by the length. So in the particular case of a cylinder, we'll need to work out the number of minutes it will take to completely fill the tank. Given this to the nearest minute, as said before, we need to know this formula. So the volume of a cylinder is the area of the end of it, circular end of course, multiplied by the height. In terms of a circular end, we're told what the radius is. So we know the radius is 15. We can use that to work out the area of a circular end in a moment. And the height, we're told, is 43 centimeters. And it's labelled there for us as well. So if we were to just type this into the calculator, the area of a circle is pi multiplied by the radius squared. So the area of the circular end will be pi multiplied by 15 squared, and then we multiply that by the height, which is 43. So if we try this on our calculator, pi times 15, or just 15 squared, multiplied by 43. These brackets are optional. You don't need them. I'm just putting them here to make it clear what the circular end is, and the height is separate, but you don't need brackets. But anyway, you'll probably get an answer in terms of pi, which comes out to give 9675 pi centimeters cubed. If your calculator is not giving you this value, I'll just show you what you might get instead. So if I type in 9675 shift pi, with a pi symbol in here, this just means the answer is in terms of pi. To get an actual numerical answer, press SROD. If you've got 30394.908 and so on, that's fine as well. So either this value here or that one. So we're about halfway done for the problem now anyway. So we know the volume of the cylinder in total, but it's saying here about litres. Here we worked out in terms of cubic centimetres. That's a difference. So if we're trying to work out this in terms of litres rather than centimetres cubed, we need to remember the relationship in between cubic centimetres and litres. A good thing to know, well, a crucial thing to know, is that each cubic centimetre is defined as 1 millilitre, and 1,000 millilitres make 1 litre. Therefore, 1 cubic centimetre is 1 millimetre, which means that 1,000 cubic centimetres is the same as 1 litre. That's the conversion factor we need to work with. So I've not got a full litre, I've only got 0.47 of a litre. So a full litre would be 1,000 cm cubed. So what I'd suggest you might want to do first is to work out um, essentially what 0.01 of a litre would be in terms of cm cubes. So what I could do here, for example, I could divide by 100 first to find what 0.01 of a litre would be, then times by 47. If you can just do this and just see it, by all means, you could just say that therefore 0.47 litres is 470 cm cubed. To do it a bit more step by step, what you could do first is divide both sides by 100 to find what 0.01 of a litre is, and then multiply by 47, like I showed you on the calculator. Either way round, it should work out that 0.47 litres is 470 cubic centimetres. So, water's flowing into the tank at that rate. So each and every minute, an extra 470 cm cubes is in the tank. We need to get to a total of that amount, which if you remember was about 30-odd thousand cm cubes. So how many seconds, when each second fills in this much liquid, do we need to get to that total? Essentially, it's a case of how many times does a smaller number fit into a larger number. It's going to be a division question to finish off. So the number of minutes required will simply be 9675 pi divided by 470. That comes out to 64.67-ish minutes. If I show you here, so it was, if I go back to the previous answer, which was this one here, divide that by the 470. Whoops, I'll just start again. 9675 shift pi, divide by 470. Yeah, 64.67. Tempting to think you're done, but that'd be a terrible way to lose a really annoying mark, because it does say clearly here to give your answer to the nearest minute. So 64.67 is closer to 65 minutes than 64. In other words, we're going to round up because 6 is 5 or higher. Therefore, our final rounded answer is 65 minutes to the nearest minute. Question 8 is about an error interval. So a weird name, error interval. I'll quickly explain what an error interval means. Error means potential, obviously, mistake or inaccuracy, and an interval essentially is a gap. So it needs a beginning and an end. So a number's been rounded, and it's ended up being rounded to 1.9. So your best guess would be the number would be 1.9. Obviously, it's incredibly unlikely it would be exactly that. So your best guess is it's 1.9. But then if that is your guess, where could your actual number have begun in terms of how small it may have truly been and how big may it have been before it was rounded is known as the error interval. So what we need to consider is what number, having been rounded to two significant figures, would have rounded up to 1.9. What's the smallest thing that would have rounded up to 1.9? And what's the absolute maximum upper limit between rounding up to 2.0 or rounding down to 1.9? Well, the biggest clue here is it's been rounded to two significant figures. So imagine, for example, it's a two-digit number. Well, it's in terms of with the decimal included, I mean. So the first two-digit, two significant figure number we could have, for example, would be 1.0. So if you imagine a number line going up 0.1 each time, been rounded to two significant figures, 1.0, 1.1, 1.2, 1.3, and so on. If you imagine a portion of that number line with 1.9 in the middle, something like this, then the actual number could have been anywhere along here, but it's been rounded correctly to 1.9 to two significant figures. That means the number must have been closer to 1.9 than either 1.8 or 2.0. So let's think about what the halfway points would be in between 1.9 and the lower bound, or 1.9 and the upper one, 2.0. So if I just fill in the halfway values here, between 1.8 and 1.9 is 1.85, and halfway between 1.9 and 2.0 is 1.95. So clearly, the actual number must have been somewhere in between these two values here. So I'm going to draw in these lines. Now, if a number were 1.85, that would round up, of course, to 1.9. The old rule from primary school, if it's 5 or more, we round up. So at 5 would cause the 8 next to it to round up to a 9, which is great. For 1.95, however, if it were truly 1.95, that would cause the number to have rounded up to 2.0. So 1.95 is the cut-off point, which you're not allowed to have. You can be as close as you want to this line, but never quite touch it. Whereas 1.85, you can actually have that value, and that's fine. That's why this is a filled-in line, to emphasize that 1.85 is allowed. It's an allowed limit. 1.95 is a dashed line, which signifies it's a limit we're not allowed to actually touch upon. So the number, before it was rounded, must have been in between these two boundaries. So the error interval is in between 1.85 and 1.95. However, an error interval is actually an inequality, essentially. And as I said, it would go in between this thick red line and the dashed red line, like so. Now, an inequality on a number line would be given using circles, either filled in or dashed. Because we're allowed to have 1.85, this would be a filled-in circle above this boundary. And because 1.95 is not allowed, that would be a hollow circle. So in inequality notation, not the question's asking this, but if you're interested, that would be what the inequality would look like, the error interval for x. Anywhere between 1.85, which is allowed, all the way up to, but not including, 1.95. You get 1 mark for 1.85 in the right place, 1 mark for 1.95 in the right place, and 2 marks for your answer looking like this. And again, the inequality symbols are crucial. X is allowed to be 1.85, hence the line underneath there, that's okay, but it's not allowed to be 1.95, hence no line underneath the inequality symbol at the higher boundary. Question 9 is expanding 3 lots of brackets, so expanding triple brackets. This is a nice skill to know. Essentially, you can only expand 2 lots of brackets at once. So just pick any 2 of these 3 brackets to expand first, get your answer to that and simplify it, then the answer to that, then multiply out by the bracket you've not yet expanded. So, like I say, you can pick any 2 brackets you wish out of these 3, but just keep it simple. I always use the same technique. I do the last 2 first, and then finish off by doing the answer to the expansion of the last 2 multiplied by the first bracket. So as I say, you can do them in any order, but I'm going to choose to do the last 2 first. So I'm going to expand x minus 2 and x plus 3. So even though you can do this in a few different methods, my preferred method is the grid method, which I'm going to show you. I know there's FOIL and the crab claw method and all different ones, but I think this is the best way personally. So I'm going to multiply x by x, gives us x squared. X multiplied by minus 2 is minus 2x. X times 3, 3x. And finally, 3 times 2 is 6, so 3 times minus 2 is minus 6. This then needs to be simplified down. We've got 1x squared. 3x take away 2x just leaves us with 1 positive x, and of course minus 6. So the expansion to the last 2 is x squared plus x minus 6. We're now going to multiply this x squared plus x minus 6 by the x plus 7. So now we're going to do a new grid, but this time, because I'm multiplying these 3 terms by the first 2 in the bracket I've not yet touched, I need to do a 3 by 2 grid, something that looks a bit like this. So the answer to the first expansion multiplied by the bracket you've not yet expanded, which, like I've said, the first one is one I've not yet touched. So again, these boxes can be done in any order. I normally pick the top left first. So x squared multiplied by x, x cubed. X multiplied by x, x squared. X multiplied by minus 6, minus 6x. 7 times x squared, 7x squared. 7 times x is 7x, and 7 multiplied by 6 would be 42. Because it's a minus 6, we get minus 42. Now we just need to simplify this down, and then we're done. So we've got 1x cubed. They simplify down in this pattern here, going diagonally, which is quite nice. We've got 1x cubed. We've got 8x squareds altogether. 7x's take away 6x's combines to be 1x overall, and then minus 42. So fully simplified, we've got x cubed, plus 8x squared, plus x minus 42. And that's your final simplified correct answer. If you've done it in a different order, that should still be the same answer you get for yours. If you put 8x squared first, that's okay. The most important thing to secure all 3 marks is that the numbers in front of the x's, whether it be cubes, squareds, or normal x's, are correct, and the signs are correct as well. So, for example, 8x squared plus x cubed minus 42 would also be full marks, for example. But that's question 9 done. Question 10 relates to probabilities, in particular tree diagrams. So we're told that Shakir has to complete 2 tests, unfortunately for him. He can either pass or fail, so there's no chance of somewhere in the middle. It's either pass or fail, only one or the other outcome. The probability that he will pass the first test is 0.87. Part A, just skipping ahead, it says complete the probability tree diagram for the information. So even though this has been added on, it does say here the probability that it will pass the first test is 0.87, which is why this 0.87 is here, like so. But what we need to remember is each fork, each sort of set of prongs, if you like. For example, this is, in my head, I call this a fork because it's like 2 branches. This is a second one. This is a third one. Each set of forks, each set of branches emanating from a single point must all add up to 1. So if this is 0.87, whatever the probability is of failing, when added to 0.87, must equal 1. So the chance of him failing the first test would be the other 0.13. In other words, 1 minus 0.87. So we can say that the probability of him failing the first one, therefore, must be 0.13. So we can add this onto the diagram. Double check, 0.87 plus 0.13 does equal 1. We can now use this other bits of information to complete the tree diagram. So it then says about the second test. Well, if he passes the first one, the chance he passes the second is 0.94. So that's if he passes the first. So looking at this top set here, this top scenario. So if he passes the first, chance he also passes second is 94%. So here, which I've highlighted in this light blue, needs to be 0.94. In the same way again, because this is a set of branches, the bottom one plus the top must need to add up to 1. So 0.94, imagine that as 94 pence. So what added to 94 pence gives us a full unit to pound, needs to be an extra 6 pence. In other words, the probability of him failing the second if he passes the first is 0.06. So we can add this on as well. Then finally, if he fails the first one, the chance he passes the second is 0.73. Presumably that's lower than 0.94 because if he fails the first, his confidence, sadly, has been hit. He's not feeling as confident, perhaps, who knows. Anyway, we can add this on here. So if he fails the first one, the chance of him passing the second is 0.73. So here, we're going to add in 0.73, which I've highlighted in this dark orange. Therefore, hopefully you can see now something plus 0.73 needs to equal 1. So the value for him failing the second one, if he fails the first, must be the extra 0.27. In other words, 1 minus 0.73. So down here, we're going to put 0.27. So that's part A complete, because all the values on each branch have been complete. For part B, it says to work out the probability that Shakir passes at least one of the tests. So this can be done in a few ways. It doesn't say he's passing exactly one, just at least one. So he could pass both. So there's actually 3 different routes, 3 different scenarios in which he could pass at least one test. So let's just list them. The chance of him passing at least one, well, he could pass them both, pass and pass, or he could fail the first and then pass a second, or alternatively, he might pass the first but then fail the last one. So let's just consider these routes. I'm going to add them onto the diagram. So pass and then pass is this very top route here, which I'm going to highlight in red. So if he passes and then passes, if it's an and, where it's one event and then the other, we need to multiply these probabilities as we go along the branches from left to right. So the chance of passing the first and then passing the second will be 0.87 multiplied by 0.94. The chance he fails and then passes is fail and then pass. Or the chance he passes and then fails is this green route here. It's like we're saying pass and then pass would be the 2 numbers you cross-passed along this red route. So that's going to be 0.87 multiplied by 0.94. If you try that on your calculator, that comes to a value of 0.8178. So essentially, in plain English, there's about an 82% chance he passes both tests. Or he could he could fail and then pass. So failing first, 0.13, and the second number we pass is 0.73. So as we move from left to right, we multiply the values together. So the chance of failing and then passing will be 0.13 multiplied by 0.73, which should come out on your calculator to give 0.0949. The final option is pass and then fail. The two numbers we pass by here are 0.87 and 0.06. Another way I sometimes mention to my students is pass and fail. The word and in probability will almost always imply a multiplication. So pass and failing is the pass value multiplied by the failing probability. In this case, 0.87 multiplied by 0.06. And again, if you try that on your calculator, you should get a value of 0.0522. The last thing we need to do is just add together these three values, which I've color-coded in red and then blue and then green. Add them all together, you should get 0.9649. Now, other teachers might disagree with me and think there's a much easier way of doing this. And I sort of don't disagree with them, to be honest. An easier way, if you can get the concept, is to realise that, well, there's actually only one way he couldn't do this. So if he just needs to pass at least one, there's only one way he will fail to do that. The only way he's not going to pass at least one is if he fails both of them. So what we could have chosen to do is to work out the probability that he fails both. Fail and then fail would be 0.13 multiplied by 0.27. And that would give us 0.13 multiplied by 0.27, which is 0.0351. So in other words, there's like a 3.5-ish% chance he fails both. Therefore, the other 96.49% of the time, this value here, he must have passed at least one of them. So what we could have done is worked out the probability he failed both, and then did one subtract the probability fail, fail. Because if we subtract the probability of failing both, what we remain with is all the other options where he's passed at least one. So as an alternative, it's the same as doing 1 minus probability of fail and then fail. But anyhow, question 10, the final answer is 0.9649. Question 11 is a fairly classic type of question. It's a graph matching one. So we've got graphs, 4 different ones, A, B, C, and D, and each one represents a graph of proportionality. So one of these, A, B, C, or D, will represent a graph of y being proportional to x squared. Another one represents y is proportional to x. Y is proportional to 1 divided by x. Another one is y is proportional to the square root of x. The general rule I would say is a graph of proportionality of y proportional to x squared will have the same characteristic shape as a graph of y equals x squared. So imagine these proportionality symbols as equal signs, and then be thinking which graphs look the same or very, very similar to, for example, the graph of y equals x squared, which you're familiar with. So the graph of y equals x squared is a parabola. It's a curve. It's a happy, smiley face. So the graph which represents proportionality to x squared, y is proportional to x squared, would actually be graph D. That's half of a smiley face, and of course it would go up like this. So D, whoops, that's what I meant to do there. So D is actually y proportional to x squared. So that's going to be graph D. Y being proportional to x, I want you to imagine the graph of y equaling x. For example, when x is 0, y is 0. There. So y equaling x would always be a straight line going through the origin. The only one which is a straight line going through the origin is graph A. Therefore, y being proportional to x has to be the only one that looks like y equals x, which is graph A. So y proportional to x matches to A. This one here will look similar to the graph of y equals 1 divided by x. So if you imagine x being really, really small, like somewhere here, and imagine it being a graph of y equals 1 divided by x, you have a calculator. It's a calculator paper. So if you try 1 divided by something really, really small, gives you something really, really big. So that fits this graph. And if x is really, really big, 1 divided by something huge makes y go really, really small down here. So actually, this is graph B. A graph of inverse proportionality, inverse to x, will always look like a curve like this, where it scrapes the y-axis as it goes higher, and as x goes larger, it scrapes the x-axis but never touches. So long story short, this is graph B. And y being proportional to the square root of x, it's actually similar to y being proportional to x squared, but just switcherooed. The axes are switched. So, for example, if I just were to square both of these, it'd be y squared is proportional to x. So rather than x being squared, it's for y which is squared. So it looks like x and y switch. So it's going to be like a curve like this, but actually it's on its side. That's going to be graph C. If in doubt, just know them, just learn them off by heart, essentially. But there is a bit of understanding to these, but in a very sort of short, snappy video where I don't bore you to tears, I'm just going to give you the take home. So that's how they match. Know them, learn them, revise them with your teacher, and when they do come up in exams, as long as you remember them, they're actually fairly straightforward questions, if you have the knowledge, that is. Anyway, so it's D, A, B, C, in that order. Question 12 is about coordinate geometry. So because we've got different coordinates and different points, I would always suggest drawing this out. So if you look here, the x values, one of them's slightly negative, but all the y values are positive. So I'm going to do a coordinate grid, but just keep it where y is positive. So I'm going to sketch it out like this. Here's an x and y grid I've done before. Don't need to be sketched perfectly accurately, but just to give you an idea so you can picture the question in order to answer it. I do think this is a really mean question for only 3 marks. I think it's worth more. But anyway, I'll stop complaining. So first of all, A. A is a point with coordinates 7, 13. So it's 7 along, 13 up. So let's add this one on. So there's A. B is the point with coordinates -3, 21. So -3 about there, 21 obviously higher than 13. So B is going to be about here. Let's add that on. And finally C, 15, 23. I'm going to add this in green. 15, 23 will be somewhere up here. So let's get the points added in. It now says that M is the midpoint of AB. That means that if you imagine a line from A to B, or B to A, M is going to be halfway along that line. So because we're talking about AB, we're interested in point A and point B. So if I just return to point A for a minute, point A is 7 along and 13 up. I'm going to think about M in a moment in a purple colour. But just considering point A is 7 along, 13 up, like so. B is 3 to the left and 21 up. So if M is in the middle of A and B, we can work this out together. So it's going to be halfway along horizontally between -3, where B is, horizontally, and 7. From -3 to 7, that's a gap of 10. That's 10 units along. If I half that gap of 10 units, half of 10 is 5 units. So the midpoint horizontally along between A and B will be at 2, because 2 is halfway in between -3 and 7. So M will have an x-coordinate of 2. In a similar way, the midpoint M between A and B, if A is 13 high and B is 21 high, M is going to be in the middle of 13 and 21. From 13 and 21, that's a gap of 8. Half of that gap would be a gap of 4. And so the middle between A and B going upwards would be 13 plus 4, which should be 17, because 17 is halfway between these two numbers. So if I add on the y-coordinate of M in purple as 17, we've got what M is. M is 2 along and 17 up. So we add on coordinate M here. We can then do similar for N. n is in the middle of b and c. I'm going to do this in a pink colour. So now we're just interested in b and c. So I've added on the coordinates of b. If I do the same for c, 15 along, 23 up, like so, we can now think about what's halfway in between b in blue and c in green. So considering horizontally again, first of all. Horizontally, we've gone from -3 at b up to c, which is 15. From -3 to 15, that's a gap of 18. I need to add 3 on to get back to nothing, then nothing plus 15 gets me to 15. 3 plus 15, that's a gap of 18. Because you want the midpoint, we halve that gap. Half of 18 is 9. So in the middle of -3 and 15, that will be -3 plus 9, the gap in between them, which is 6. So the x-coordinate of the middle of b and c will be 6. In the same way, going upwards between b and c, this is quite easy to see, I'm hoping. If b's at 21 and c's at 23, the midpoint of b and c will be halfway in between 21 and 23. That's in the middle. And what's in the middle of 21 and 23? Quite obviously, it's got to be 22. So therefore, n, the middle of b and c, is 6 along, 22 up. So we can add in the n is this point here. So that's m, and that's n. The question finally is just asking us for distance in between m and n. So this diagram's now looking a bit messy. I've got 5 different points on. I'm just going to focus in on what we're interested in, which is just m and n. So if I make a, b, and c disappear for a second, like so, what I'm going to have here is just m and n. M in purple, n in pink. And between m and n, I'm going to do this in a light blue colour. The distance in between them is going to be between that purple point and that pink one. This distance here. Now, what we can do is actually think about how far along we need to go and how far up. So from 2 along to 6 along, horizontally, that's a gap of 4. Vertically, from 17 up to 22, that's a gap of 5. And I've added in a right angle here. Hopefully, you'll identify what to do now. I know that this is a triangle. It's right-angled. I know 2 sides of it, and I want to work out the third side, which is the longest, for hypotenuse. In other words, this is actually now, it reduces down after all that to a Pythagoras question. So, that longest side squared, the hypotenuse squared, will be that side squared plus that side squared. In other words, mn all squared is 4 squared plus 5 squared. That's 16, and that's 25. 16 plus 25 gives 41. So mn all squared is 41. Then hopefully you remember, with Pythagoras, the final step is always to square root. Therefore, mn will be the square root of 41, which gives an awkward, ugly-looking decimal, 6.40312, and carries on and carries on. Don't lose a mark annoyingly, though. Read the question carefully. It says, give your answer correct to 1 decimal place. The first number after the decimal is a 4. After the 4 is a 0. If that 0 were a 5 or higher, that 4 would be forced up to a 5. However, because it's a 0, we do not round up, and it just stays at 6.4. So the final correctly rounded answer is simply 6.4 units distance between m and n. Question 13 is about recurring decimals. We need to prove that this recurring decimal can be written as this exact fraction. And notice it does say prove algebraically. So we're not doing any long division on this fraction to show it equals this one. The key word is algebraically. So I'm going to highlight algebraically. And what we need to do is to set this recurring decimal equal to some letter because it's algebra. So what I'm going to say is we're going to call 0.0723 recurring, this thing here. Let's call this x. Now, recurring goes on forever, and the dots above the 7 and the 3, where the dots begin and end, that shows what the repeating block is. So the first two zeros aren't repeating because a dot hasn't appeared yet, but it appears across a 7 and stops on the 3 with a 2 in the middle. So the repeating block is 723, 723, again and again and again. So what we're going to do is say let x equal 0.0723 recurring. And what I'd always suggest to do is to write out a few repeating blocks of this and always include the dot dot dot, which in terms of English is called an ellipsis. But the dot 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 indicates to the examiner that you know that this is a recurring decimal and goes on forever. So do write out the dot 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 if you're expressing a recurring decimal in decimal form without the dots above the digits. So anyway, the technique, what I'm going to suggest we do is we start with x and we're going to multiply x by 10 and by 10 again and by 10 again and so on until we get the digits to line up. I'll explain what I mean. I would always suggest to do a grid, or at the very least make sure you write it carefully and clearly so the digits line up with your decimal points in order. So here's a grid, and these red dots are going to be the decimals. So I'm going to start at the bottom and write x. So x is 0.0723723 and so on. I'm going to now multiply this by 10 to get 10x. I'm going to write 10x in the row above. 10x is just this value multiplied by 10, so I imagine it in terms of the decimal point jumping one place to the right, and so 10x will be 0.723, 723, 723. So let's write this in. And like I say, what we're wanting to happen is for the digits from the right-hand side to be lining up and agreeing. 3 doesn't match to 2, 2 doesn't match to 7, and so on. So the digits do not line up. If they don't line up, we go again. I'm going to multiply this by 10 to get 100x. So again, the decimal will move one place to the right. So 100x will be 7.23, 723, 723, like this. That's what 100x's will be equal to. Again, none of the 3 rows we've got so far line up. 7 doesn't match to 3 nor match to 2. So again, you just times by 10 and keep going and have faith that eventually the numbers will line up. So 7.23-ish times by 10 will be 72.372, 372. Let's write this one in, making sure that you get the digits in line. 1000x is 72.372, 372, and so on and so on. But now look at the bottom and top row. From the right-hand side, the digits now do match. 2 matches to 2, 7 matches to 7. So we've got the main target now. Once you've got 2 rows that match, forget about the others, and highlight and focus on the 2 rows that do have digits lining up from the right-hand side. So I'm going to highlight the x and 1000x rows in yellow. And what we're going to do now is do the top row take away the bottom row, ignoring the 100x and 10x. So I'm going to vanish these 2 middle rows because they're not needed now. We're just focusing on the 1000x and the 1x on the bottom. So if we were to do, according to old-fashioned primary school subtraction, this value take away that value, with the dots lining up, the decimal points lining up, we start by doing 2 subtract 2, which of course is 0. In my language, 2 take away 2 cancels. So 2 take away 2 cancels off, as does the 7 and 7 here. 3 take away 3 cancels, and you've guessed it, as does this 2 and the 2 there. The final digits to cancel are the 7 and the 7, the second decimal place of each number. 7 takes 7, again will cancel, so that's what we have. The rest doesn't cancel because 3 is different to 0. However, 72.3, take away 0.0, which is nothing, that's just going to leave us with 72.3 because I'm literally subtracting nothing at all. So 1000x take away 1x must be equal to 72.3. And in terms of x's, 1000x's take away just one of them leaves us with 999x. So our equation is 999x's equals 72.3. I don't want to know the value of 999x's though. I want to show and prove that the value of just one of these x's equals this fraction here. So to get x on its own, I can divide both sides by 999. So x, write this as a decimal, will be 72.3 all over 999. So x equals this, but it's not like this at all. Bearing in mind you do have a calculator, but we're trying to prove it, so don't be too reliant on just button bashing and just writing in one step, this equals that. What I would say is just show very carefully to the examiner that you know what you're doing and you can manipulate that and show that it equals this exact fraction. I'd suggest multiplying top and bottom by 10 to get rid of a decimal at the top. So multiplying both top and bottom by 10, x must be 723 all over 9,990. Now, you know, or you should have faith that this will simplify down to that one. And again, you can check on your calculator if in doubt. You can type this into your calculator and press equals, and it will simplify down to this. All you need to do simply is to divide by 3, but then you've made it really clear to the examiner that you know this will turn into that. Therefore, x equals, as a fully simplified fraction, 241 all over 3,330, which is exactly what we wanted to prove, so therefore we've done the question. The key thing here is, because algebraically you need to call this decimal here a letter. Call it D if you don't like x, but it needs to be called a letter, otherwise you will not get the marks. Question 14. As far as question 14s go, this is really hard, I think. It's about proportion, but it's a combination of proportions. We've got y proportional to x squared, but then also x is inverse proportional to w. So this is actually quite a nasty question, but let's just take it step by step. So let's start with the first line. So it says y is proportional to x squared. If it just says proportional, you can assume it means directly proportional. So there is a symbol for proportionality, and it looks like a fish to my mind. So y is proportional to x squared. We can write it like this. This is one and the same thing as saying that y must equal some number, some constant, times x squared. So, as I often joke very sillily with my students, fish can't do maths, so we get rid of a fish, replace it with an equals and k. So this means that y equals some k, which you don't know yet, multiplied by x squared. Now, to find what k is, we use the extra information of the question and we sub in the values. So we're told that when y equals 3, x is 0.5. So if we pop in that y is 3 here and that x is 0.5, we get that actually 3 must equal some number k multiplied by 0.5 squared. Just saying that y is 3 and replacing the x with its value 0.5. Now 0.5 squared is 0.25. So this means 3 equals 0.25k, which is a fairly simple equation to solve. You can do this in a few ways. To get k on its own, you could either divide both sides by 0.25, or if you know that 0.25 is the same as 25%, you could times both sides by 4 to get a whole k. So what I've chose to do here is to just multiply both sides by 4. If you divide both sides by 0.25, that's fine as well. Either way around, you should find that k has a value of 12. So therefore, using numerical values, y must equal 12x squared. So you can write that down as our first step. So we have some marks in the bag. The next relation we have is between x and w. So I'm going to separate this out to the left and look now at this one. So x is inversely proportional to w. Inverse or direct proportion still has this fish symbol. That just means proportionality. But inversely proportional doesn't mean x fish w. It means x fish 1 over w. So inverse proportionality means 1 over what it's inversely proportional to. In the same way, fish can't do maths, so replace the fish with an equals k. So x equals k times 1 over w, but k times 1 over w we can just write simply as k over w. Now I'm calling this one big K, so it's not confused with this little k. You can use a different letter altogether if you want to. Teachers and textbooks normally use little k for constant proportionality. If you have two constants to deal with, I would suggest to pick either two different letters or maybe have a little k and a big K like I have. So this big K, to be perfectly clear, is a different K to that one. Sorry if that's confusing. But now we follow the same steps. To work out what this big K is, to get the actual full relationship, we substitute in a known x and a known w, which we have here, look. So we're told when x is 2, w is 0.2. So therefore 2 equals big K over 0.2. Again, this is an equation. I need to have K on its own. K is being divided by 0.2. The opposite of being divided by 0.2 would be to multiply by 0.2. So if I get K on its own by multiplying both sides by 0.2, we see that big K must be 0.4. Subbing in 0.4 for the letter, we now have the relation that x equals 0.4 divided by w. So we're almost done. The question here, though, asks us to find the value of y when w is 2. So we're only interested in y and w at the end of the day. We've got here y related to x. I don't care about x anymore. I want to know what it means in terms of w. So we're going to start with this thing here, that y is 12x squared. But we're going to rewrite x all in terms of w. So it's about what we're interested in, which is w. So if y is 12x squared, then we can say, therefore, because x is 0.4 over w, then y equals 12 lots of 0.4 all over w, all of that thing squared. So if I rewrite it here, y is 12 lots of x squared, which means 12 lots of all of that squared, and do wrap it in brackets. It's just the x I'm squaring, not the 12, and x is all of this thing here. So we can just sub in now that w is 0.2. So if w is 0.2, y is going to be 12 times 0.4 over 2 squared. Then we can work this out on a calculator, simple enough. So y is going to be 12 lots. I'll get the screen on for you. Whoops, where is it? There we go. So it's going to be 12 multiplied by, in brackets, 0.4 all over 2 squared, and this gives us a value of 12 over 25, which is absolutely fine, or as a decimal, we can say it's 0.48. So therefore, y equals 0.48, and that's our final answer to complete question 14. Question 15 is quite big, 3 parts, A, B, and C. Part C is on the next slide. Essentially, it's a histogram. So we've got an incomplete table and an incomplete histogram, giving information about the times taken by some students to run a race. I will pretty much say this as a fact, as something that's always going to be true. If it's a histogram, it's going to involve 3 things. The first thing is frequency, the other thing is frequency density, and the other thing is class width. Now, class width is just a fancy word for just explaining how wide each of these bars are. So what I would suggest to do for this table is to add in another couple of columns for class width and frequency density. And these 3 things relate in a very, very important formula, which is as follows. I'll explain the graphic in a second. You might be thinking, what on earth am I doing here? Frequency density equals frequency divided by class width. I've got here a fairly large man looking very temptingly at some chicken wings. This is just me being very silly because it helped me to remember. I always say, fat dads feast on chicken wings. Just a way of remembering the relation. You don't need to be silly like me. As long as you can remember frequency density is frequency over class width, that is fine. But feel free to use that very silly way of remembering if it does help you. So what we can do now is actually use this relation to fill in the table. So we don't know the frequency density scale yet. We don't know what this is going up in, but we do know the class widths. So for example, from 10 to 12, that's a width of 2. From 12 to 16 is a gap of 4. From 16 to 19 is a gap of 3, and so on. So if you fill in all the class widths just by looking at these gaps here, that's all I've done. And then what we can do, using the bars we've got frequencies for, we can use this formula to work out the frequency density of these 4 bars. So because frequency density, which is basically how high the bars are, is frequency divided by class width, we can use a calculator to do this column divided by that column. For example, 10 divided by 4, that's going to be 2.5. 15 divided by 3 will be 5. 9 divided by 2 is 4.5. And 7 divided by 5 will be 1.4. So you should get those values using your calculator. Now what we can do is we can actually look at a bar we know and work out from that it's this scale on the frequency density. The first bar from 10 to 12, well, we don't know what the frequency density is for that one, so we can't use that bar. However, from 12 to 16, the second bar that's been drawn on, we do know that's got a frequency density of 2.5. And so this height here, at this point, is exactly 2.5. Now let's see how many big squares high that is. So if that's 2.5, I've gone up 1, 2, 3, 4, 5 of these big 5 by 5 squares. So if 1, 2, 3, 4, 5 gets us to 2.5, each one of these squares must be worth 0.5. 0.51, 1.52, 2.53. So we can label on our scale now for the frequency density. And the scale is like this: 2 big squares per unit of frequency density. Now we have worked out the scale on the frequency density, the y-axis, we can use that scale to actually calculate and work out the height of this first bar from 10 to 12. From 10 to 12, we can see there it's got a frequency density now of 1.5. So if I add in here 1.5, I can then work out its frequency using the same formula again. If I cover up frequency, frequency is just going to be frequency density multiplied by class width. So in our case, 1.5 multiplied by 2, that means from 10 to 12, that represents 3 people. So part A, it said use a histogram to complete the table. We have completed the table. The missing value for frequency was 3. Part B, we're now going to use our completed table to complete the histogram. So from 10 to 12, yeah, we've got that bar. We've got 3 bars done, which relate to the first 3 entries in this table. We're just missing the final 2 bars from 19 to 21, and then from 21 to 26. So from 19 to 21, we need a bar which is 4 little squares wide. That's 19, that's 20, that's 21. And it needs to be at height of 4.5, so it needs to be up here. So it's going to be 4 little squares wide up at 4.5. So the first bar needs to look like this. And no, it doesn't need to be coloured in green. I've just done this here to make it clear for the video. The final one, from 21 to 26, which is going to end there, that needs to be 1.4 high. So it needs to be up to this point here. So it needs to be a rectangle like so. Here's one I made earlier. And that's what your completed histogram should look like too. Let's now have a look at part C for question 15. Part C looks at a different histogram for a different race. So here is a different histogram for times taken by 43 students to run a different race. We need to work out an estimate for the median of the times taken by these 43 students to run the race. Go to the basics first. What does median mean? Median is the middle. So what was the middle person? So if there's 43 people, I want you to imagine 43 people in a line from the slowest to the fastest, or from fastest to slowest, whichever way around. So I've got here these 43 students. You don't need to do this. This is just for me to illustrate to you. These are 43 dots with a big blue dot in the middle. So imagine 43 students in order of finishing. These might be the fastest here, the slowest person down there. So the fastest 21, the slowest 21, 21 plus 21 is 42. So that means there's one person in the middle and 21 either side. In other words, the median student is going to be the 22nd. 21 faster than them and 21 slower. So we need to work out which bar this 22nd student is represented inside. It's still a histogram though, remember it's a different one, so we still need to use the same formula that frequency density is frequency divided by class width. We can see the class widths, we can work these out. So if that's 10 and that's 15, halfway between 12 and a half, so that must be 12. So each little square going along must be 0.5. So that's got a width of 2, that's got a width of, well, you can work the rest out. But what you should find, if I just label on these points here, that the first class width is 2, then 4, then 4, then 2. and then 4, which I'm just labeling on here for class widths. We've got the frequency density labeled as well, so we can just take the density and times our class width to work out the frequency represented by each bar. So the first bar, 2 by 2, that gives 4. Just covering up frequency to do these two here. So 2 times 2, that's 4. This bar is 4 wide, 2 high. 4 times 2, that represents 8. And this bar here is 4 wide and 4 high. 4 times 4 gives 16. I could, of course, work out the frequencies represented by the final 2 bars, but because I'm only interested in the median, I don't need to go the whole way along. I just need to work out where I get up to the 22nd student. So 4 plus 8, the first 12 students are represented in these first 2 bars. The 22nd student will be these 12 plus another 10 students after. So the 22nd student will be the 10th student after these first 2 bars, because 12 plus 10 gets us up to 22. So I want an extra 10 students after these first 2 bars. But this bar here represents 16 students in total. So I want the 10th student out of a total of 16 to get to the 22nd student overall. So the median one is going to be the 10th value out of 16 in this bar here. What I'm going to suggest we do, because it's 10th out of 16, sorry for almost shouting, if it's out of, think of it as a fraction. 10 out of 16 is 10/16ths, which simplifies to 5/8. So obviously the first person in this category, in this bar, would be over here. The 15th person would be towards the end of the bar. So 10th out of 16 is just over halfway. That's where the 22nd students overall, the 10th one in this bar, would be. And you can even count it up in a fairly babyish way. There's nothing wrong with doing that. For example, if this here is the 12th student and then over 16 in total, then how many little squares represents 16? Well, it's 1, 2, 3, 4, 5, 6, 7, 8. If 8 little squares along gets us to the full 16 students, then each little square we go along must be representing an extra 2 students. Quite literally, I'm going to draw a line, the 5th little square along, out of the 8 little squares that make up the full width of that bar. So I'm going to split this bar just over halfway, 5/8 to be precise, to work out whereabouts the actual median time is. So 5 little squares out of 8, literally 5/8 of that bar. The median time, well, the estimate for the median is this point here. So just work it out very carefully. If that's 16, 17, 18, you should find, if you're very careful, that's 18.5. So split this bar, 22 students that side, the others on that side, so the 23rd is bang here. And that's going to be at the point where it's 18.5 seconds. So our best estimate using proportional reasoning is that the time for the median student was 18.5 seconds. Question 16. So ABCD is a trapezium, as shown on the right of the screen. AD is parallel to BC, so that's a key piece of information. Calculate the area of triangle BCD. So we want to work out the area of a triangle on the right, not this one here on the left. It says give your answer to 1 decimal place. So I'm going to start by suggesting we use this piece of information that AD is parallel to BC. So if we do that, we can actually use an angle fact. So if I just add in AD and BC with these blue lines, we can use the idea of alternate angles, which I term as Z angles. So if I imagine a Z, well, sort of like an N really, but an N upside down from here, then from D to B, then B down to C, we're making a Z angle, technically known as an alternate angle pair. So essentially, if this is 42 degrees, we know the angle here at B will also be 42 degrees. And the reason we can say that is the following. So angle BDC, this one is the same as angle ADB. because alternate angles are equal. Now, we don't need to say that to the examiner. The question isn't asking us for angle proofs or to state reasoning, but if you want to know, that's why we do know and can deduce that this angle here is 42 degrees. So because we can work that out, we may as well add it to the diagram. So moving on, I'm just going to get rid of that triangle for a second, because if I just go back to it actually for a second, there's not enough information for us to tackle the question. If I just go back to BCD here, there's not enough information we know about this triangle to work out anything useful, especially not its area. So what we're going to need to do first is to see if we can work out something which relates both triangles, then apply it to the one on the right. In other words, if we just focus in on the triangle we know more about, we can return to this one later. So again, like I said, I'm going to get rid of this triangle and focus on this one over here. Now, you should be able to spot, just focusing on this triangle, we know an angle and the side length opposite to it. And if we know that with a triangle, and it's not a right angle triangle, that we can use the sine rule. As long as we know one extra piece of information as well, which we do, we know an extra angle. So the sine rule we can use. And if I colour in dB in purple, like so, and highlight 7.9 in yellow so it matches with this one, that's a side and angle pair. Just as this unknown side here, which we're going to call A, and 112 make another side and angle pair. So the sine rule is the following. A over sine A, where the little letters are the sides and the big letters are the angles opposite. So side A over the angle opposite to side A is the same as side B over the sine of the angle opposite to side B. Sometimes this formula confuses people because it's got three different fractions. I say to my students, you only really need two of the fractions at any one time. The fact there's three just emphasises that it can use any one of the three sides and angle pairs which are present in any triangle if you were to know them. But almost always you only need to focus on two, just like here. This is one pair in yellow, the other pair in green. So if it makes it easier for you, ignore the C over sine C bit and think of it just as A over sine A equals B over sine B. I've labelled them as such, so if we sub in to this formula, we get that side A over sine of 112 must equal 7.9 divided by sine of 42 degrees. I'm just going to colour it in green so you can see where the substitutions come from. That's A and that's 112. That's 7.9 and 42 degrees. If I now multiply both sides of this equation by sine of 112, it rearranges to the following. We get A equals 7.9 over sine 42 multiplied by sine of 112. Now, if you try this on your calculator, you'd get the following. So type in the fraction button, 7.9 all over sine 42, close the bracket off as well, move right, times sin for sine 112, close bracket. We get 10.94667077. Don't round it too soon, because that's not the final answer to the question we're being asked. We want to actually work out the area of this other triangle we've not yet even touched yet. So don't round it to 10.9. If in doubt, give it to at least 4 decimal places for now. So I'd say leave it to at least 4 decimal places. I'll give it to 5 here with dot dot dot, just denoting that actually this is going to be irrational and this decimal would go on probably forever. So now we know that A is 10.94667. We can actually substitute this into this trapezium diagram. So if I swap out A and replace it with 10.94 and so on, we now might have enough information to work out the area of a triangle in question. So if I now bring it back and get rid of the one we've just been working on, that one served its purpose. It's generated the information we need, so we don't actually require that triangle anymore. We can now see we have a triangle. We know an angle of it and the lengths of the two sides surrounding the angle we know. If ever you have a triangle, and this is the case, where two sides are known and the angle in between them, we can use the formula for the area of the triangle, which is given in the formula book So the area of triangle BCD, the formula we're going to use is this one. Area of triangle is half AB sine C. It reads much more complicated than it actually is. All it means is it's half times one side times the other we know, times the sine of the angle in between the known sides. As long as the angle is in between two sides we know, we can just substitute the sides in any order and times by sine of 42, as long as you do half of all of that. So subbing in that A is 10.94 and so on, B is 15.3, and the angle C is at 42 degrees. A, B, and C like this. We can just work out this on our calculator. Half times 10.94667 times 15.3 times sine 42. So what I'd suggest we do is this. So because we've actually got the side length, I can just press A and S to get that back. So it's going to be 1/2 times A. So I'm just going to put A and S because that was the last answer I had. That was the exact side length. Times 15.3, that one there, times sine 42, close brackets. We get here an answer of 56.0343 and so on and so on. But just be very careful to read the question. We want our answer correct to one decimal place only. So it's either going to be 56.0 or maybe 56.1. However, because next to this 0 is a 3, which is less than 5, we do not round up and we just keep the 0 as it is. So to one decimal place, our final answer is 56.0 centimeters squared. Question 17 is iteration formulas. And these sort of follow a fairly standard pattern, so they're fairly decent to revise. So if you have, then these should be not so bad should they come up. So the first part is fairly standard. We're given a cubic equation, and we need to show it's got a solution, which I suppose in plain English is like an answer, in between x being 1 and x being 2. So maybe a value of x which satisfies this is like 1.3 something or 1.4 something. Who knows? And to be honest, who really cares? The general idea is we sub in one value of x which is given to us, and then the other. And then if an answer goes from being negative to positive, or from positive to negative, that proves that the answer must be somewhere in between. In other words, the answer is between these two values if the answer changes sign in between them. So let's start off with substituting in the first value. So x being 1 and x being 2. So when x is 1, this equation becomes 1 cubed plus 2 lots of 1 minus 6, which is minus 3. So that answer's clearly negative. It doesn't even matter if it was negative a million. The main thing is it's negative. The next one, when x is 2, we get 2 cubed plus 2 lots of 2 minus 6, which is 6, which is positive. So it's gone from negative to positive. So this is important. This is what we need to say. I've put it in red. We now say because there's a change of sign between x being 1 and x being 2, there must be a solution in between x being 1 and x being 2. You'll see this more in A-level. That's not necessarily the only solution. In fact, very rarely, but it's just the only one solution. But it's very likely that there's more than one. But all we need to say here is that between these two values you've subbed in, there's a change of sign, therefore a solution in between these two values. Part B, again, is a fairly standard type of question for this sort of problem. We need to show that this cubic can be arranged into this equation. What I'd suggest doing first of all is to see if you can work backwards from this to end up with the initial equation. Then you'll see how you got from this to the one you want to prove. So what I'd say here, like I said, is to start and sort of work in reverse. So clearly that's nothing like what we start with. We need an x cubed. We've got an x and an x squared. So you might want to be thinking, well, x times an x squared would give us an x cubed. So the clue here is to multiply both sides by all of this denominator. Multiply by the bottom of this fraction, So multiply both sides by x squared plus 2. The left-hand side becomes x times x squared, which is x cubed, then also x times 2, which is 2x. We'll expand this out in a second. So x lots of x squared plus 2 equals 6. Expand it out. You'll see that it's getting fairly close now. We've got the x cubed and the 2x like we need, but the 6 is on the wrong side. So therefore, if we were to subtract 6, we'd end up with what we've actually got. X cubed plus 2x minus 6 equals 0. We can now reverse what we've done and answer the question. So starting with x cubed plus 2x minus 6 equals 0, we actually add 6, going in reverse, to get x cubed plus 2x equals 6. We could now factorize it like I've shown here to make it clearer. X lots of x squared plus 2 equals 6. Then finally, the opposite of multiplying by x squared plus 2, we can divide both sides of this by x squared plus 2. So now finally, divided by x squared plus 2, we arrive at x must equal x over x squared plus 2, which is what we wanted to prove, and so we're done. The final one, part C, we start with x subscript 0. That's just essentially saying the first value of x we're going to try. So the first value of x being 1.45, we're going to use this iteration formula here twice to find an estimate for the answer of this equation here. We're going to give our answers correct to 4 decimal places. An iteration formula is just a fancy way of saying a formula you can use again and again and again, and if the iteration formula works correctly, it will zoom in on a correct solution. So let's try this here. So using the first value, x subscript 0 being 1.45, we're going to get this if we sub it in. So the first one, the next value of x, 0 plus 1, x1, will be 6 over x0 squared plus 2, which is 6 over 1.45 all squared plus 2. So if we try that, what we're going to get is 6, 1.45 squared plus 2, press SROD, 1.462522852. We want our final answer to be super accurate. My strong suggestion is to not round the first answers off at all. Write that down in its entirety. So that's the answer we get first of all. So I've used the formula once. We need to use it again, and then we're done, because it says to use it only twice. So the next one is going to be x subscript 2. And in the place of 1.45, we now use this updated x1 in its place. So you just keep putting in the previous answer again and again. There's a quick way of doing this on a calculator, however. So x subscript 2 is that algebraically. In terms of actually what we're going to do, we're going to sub in that x1 is 1.462522. However, on a calculator, we can just use the answer button to do that quickly. So on our calculator, all we need to do is we can toggle back using these buttons here. We can delete what we had, then press ANS, so that squared plus 2, and our updated answer is 1.44964,937. However, we want this to 4 decimal places. Look, not all of this. So 4496. Does that 6 round up to a 7? No, because next to the 6 is only a 3. So we're going to cut it off after that 6. It's just going to be 1.4496 when properly rounded. And that's our final answer to part C. So that's A, B, and C completed. So that's all of question C. Sorry, all of question 17 done. Question 18. In my opinion, this might be the hardest question on the entire paper. It's not the last one, but I do think geometry involving vectors is quite tricky, or can be. Anyway, let's get to it. A, B, C, D is a quadrilateral, just a fancy way of saying it's a 4-sided shape. E, F, G, and H, which have been labelled here, they are the midpoints of the sides AB, BC, CD, and DA respectively. So the direction vector going from A to H, we're going to call that vector A. So from there to there is vector A. From A to E is vector B. From D to G, this one here is vector C. So if I just color code these right now, so I'm going to use blue for AH, red for AE, and green for DG. Just put these on like so. And I'm also going to use the fact now that E, F, G, H are midpoints of these. So what that means is if from A to E is B, then E to B, for example, will also be B, because E is a midpoint, so from E to B will be the same length and the same direction as from A to E. And with vectors, if a vector is the same length and the same direction as another vector, then it's one and the same thing. So this one here will be vector B. From H to D will be the same as A, and G to C will be vector C. So I'm going to label these on as well. So we've got a fairly good picture now of what this quadrilateral is in terms of the vectors. What we don't know yet is BF and FC. I'll come to that in a moment. So what we need to do for this question is to prove using vectors that EFGH is a parallelogram. So if I just add on the shape E, F, G, and H by drawing straight lines from E to F, then F to G, and G to H, then back up to E, it might help give us an idea of what we're trying to prove. So you can see that may well be a parallelogram just by looking at it. And we sort of know what we're going to try and prove now. We need to remember what makes a parallelogram a parallelogram. Well, in its simplest form, we can just say that a parallelogram is a four-sided shape where the opposite sides are the same length and the same direction. So that's what we're going to need to prove. We're going to want to prove that the vector E to F is one and the same as the vector from H to G, and we're also going to want to prove that the vector representing EH is one the same as the vector FG. If we can prove that, we've proved that the opposite sides are the same length and parallel, and we've therefore proven that the full thing is a parallelogram. I'm now going to return to this problem of B to C, which hasn't been labelled. So let's just think about from B to C first. Well, B to C is comprised of B to F, I suppose we could say. That's BF, and that's from F to C. But because F to C is the same length and direction as BF, because F is a midpoint, then that's BF, and this is also BF. So we can call it the same thing rather than overcomplicating it and calling that something else. And BF plus BF, the full thing, of course, is a vector BC. So let's now think about this parallelogram. What I need to do first is to consider what BF is. So BC, which is two lots of BF, let's think about how we can get from B to C. I've put on here how we do that. So we can only go down directions or vectors which we know. So to go from B to C, let's just trace it out with this cursor. I can go from B to A, like so. Then once I'm at A, I can go from A to D. Then once at D, I can go up from D to C, which is what I wrote here. So from B to C, we can go BA, then AD, then DC. So that's in terms of the points of the shape. So let's now fill it in with vectors. Well, from B to A, I'm going against the direction of B. So if I'm going the opposite direction, that's minus B and another minus B. It's the same length, so it's still just one unit of B, but because it's opposite direction, instead of positive B, it must be negative. So B to A is negative 2B. A to D is along the same pointing direction as vector A, so that's still positive 2A, and D up to C is the same direction as vector C, so that remains positive. So in vector form, BC is minus 2B plus 2A plus 2C. So if I wanted just BF, which is half of BC, then BF would be half of all of that. So half all of this, half of minus 2b is minus 1b, half of 2a is just 1a, half of 2c is just vector c. We've now got all of the ingredients to work out, using all components, what all of these lines on the parallelogram are represented by using vectors. So I'm just going to use these directions here. You could do it the other way around if you wanted, but let's just think of it now, step by step. So from E to H, I've picked first. To go from E to H, I could go to A, I could go EA, and then from A to H. From E to A is negative B, because it's going in the opposite direction, and then vector A. So EH is minus B plus A. And now I need to prove that from F to G is the same thing as that. If I can prove FG is the same as EH, I've proven these opposite sides are parallel. So now let's now think about how I can go from F to G. Well, if we look at it here, from F to G, I go F to C, which is BF, and then minus vector C, because it's against the direction of vector C. So now we've worked out what BF is. So BF is this, which you can substitute in. So F to G, I can rewrite as this. So BF is minus B plus A plus C, and of course the minus C. The C's can cancel. Plus C and negative C we can just cancel off. And so that just leaves us with, of course, minus B plus A. So I've proven that side EH is the same as FG. So that's half of my proof done. So it's worth just noting to the examiner to be very clear that I've proven it, so the examiner knows exactly what you are talking about. It's about playing the game in the exam to an extent. Now we can focus on the other pair of sides. So now let's think firstly about HG. From H to G is vector A plus vector C. If we see here, we can go from H to G by going first from H to D, which is A, then up to G, which is along vector C. So I go A and C. Now let's consider E to F. Well, E to F is going to be B and then plus BF, like so. But BF, again, we know what BF is. BF is minus B plus A plus C. So if I substitute this in now, I've got this. And then, this time, the B and the negative B would cancel off. So again, that's just going to leave us, after cancelling, with just simply A plus C, which is the same as what HG is, which is what we wanted to prove. So therefore, HG is the same as EF. These two pieces together essentially have completed the proof. We just need to clarify and conclude with a carefully constructed sentence to make it as clear as we possibly can to the examiner that we know we've done the job as intended. So, looking at these two here, one pair of sides is parallel, and the other side of opposite sides is parallel to and of equal length. So therefore, EFGH is a parallelogram, and I'd suggest to put something along these lines after as well, just to make it absolutely clear to the examiner that you know what a parallelogram is. It's a parallelogram because we've proven that these opposite sides are equal length and direction. That's question 18 done, and I think that might be a contender for the hardest one on the entire paper. Question 19 is about functions, in particular composite functions and then inverse functions. So what we've got first of all is two functions listed. F of x takes an input x, doubles it, adds 3, then the whole thing gets squared. And then other function g of x takes x, doubles it, then takes away 1. That's what's actually happening. That's how it's wrote algebraically, but what I've explained is what's actually happening to the value you put inside. The first question is to find gf of minus 3. Now that looks more confusing than what it actually is. It means we're going to do g of whatever the f of minus 3 is. So we work in the opposite direction. We work from the back to the front. So we need to work out what f of minus 3 is first, and then we apply g to that value. So I'm just going to focus in on what f of negative 3 is. So that's what f of x is, the function. So what I tend to do is to put the x inside its own bracket. So f of x, or f of whatever, is 2 lots of whatever plus 3, then that whole thing gets squared. So if instead of an x, our input is negative 3, all we do here is just erase the x and put in its place a negative 3, like so. So putting in negative 3, we can see that f of negative 3 is 2 lots of minus 3, then add 3 squared. It's a calculator paper, so by all means just type that in exactly as it looks on your calculator. I'll explain what it is. 2 lots of negative 3 is minus 6. Minus 6 plus 3 takes us to negative 3. If it were minus 6 degrees Celsius and then gets warmer by 3 degrees, it'd then be negative 3 degrees Celsius. So negative 3, then all squared. A minus times a minus makes a plus. So minus 3 multiplied by minus 3 gives positive 9. So therefore f of minus 3 is 9. We're now going to do g of f of minus 3, which is g of 9. Because f of minus 3 we can simplify to just being 9 because we worked out that's what it is. So what does g do? Well, g takes the value x, doubles it, then takes 1. So in other words, g of 9 is 2 lots of x, which is 2 lots of 9 in our case, minus 1. That's 18. 18 take 1 is 17. And that's our final answer to part A. Part B, g of minus 1 of x. Now, this is just notation. You might know from laws of indices that something to the minus 1 is the same as 1 over that value. For example, 2 to the power minus 1 is 1 over 2. It's a half. This doesn't mean that. This is just a notation, just how it's written, to do the inverse function. So what this is wanting us to do is, given what g is, how do we undo what's just happened to it to get back to the original value? So we're going to take g and work in complete opposite steps. So let's start with g itself. So g takes x. The first thing that happens to x is it runs into this 2, which doubles it. So x comes along, gets multiplied by 2 to give us 2x. We then take away 1, and that is what g of x is. That gives us g of x. We're now going to start at this side, input x, and work back to front. So if I were to take g of x and undo it, again the opposite way, instead of minusing 1, we'd add 1. And at this stage, the opposite of multiplying by 2 would be to divide by 2. And out we'll put not g of x, but because we've gone the opposite way, it's g minus 1 of x. So just think about what we've done. We've taken an unknown value, we added 1 to it first, then that whole thing we divided by 2. And that gives us g minus 1 of x. And that's our final answer. In other words, g negative 1x, the inverse of g is x plus 1, all divided by 2. Question 20, algebraic fractions. It looks absolutely disgusting, this question, but just remember, all we're talking about really here are fractions. So let's just remember the basic rules of fractions and don't lose our heads. So fractions, and another word beginning with f, factorizing. That's going to be key to this question. So we're going to write this awful looking beast in this form here, which is so many lots of x plus something all over so many different lots of x plus or minus something else. A, B, C, and D are integers. So in other words, A, B, C, and D are whole numbers which are allowed to be negative. So let's just take this step by step. You're probably thinking this bit here is the bit of it which looks absolutely horrible, and you'd be right. So if I just focus in on the horrible bit and make it look less horrible for now. I've got something divided by a fraction. So how do we take something and divide it by a fraction? Different schools and different teachers teach this in different ways, but you've probably heard keep, change, flip, KCF, almost like KFC, but not quite. In other words, if you divide by a fraction, it's the same as multiplying and then we keep the first bit, sorry, we change the division to a multiplication sign, and we flip the fraction we're dividing by upside down. So we can transform the question, keep this bit as it is because that's outside of what we're talking about, but this bit here, keep, change to a multiply, and flip the original fraction on its head, like so. It still looks a bit awkward, but at least now we can actually carry on and do something with it. This bit's a fraction, this bit isn't. How can we make a non-fraction into a fraction? Well, we can always write it all over 1. That's what I'm going to do in a second. So, as well, this first bit here, with algebraic fractions, if you can factorize something, do so. 3x minus 21, this part here, because 3 and 21 are both in the 3 times table, I can factorize out of 3, open brackets, put an x in, because 3 times x gives us 3x, and that's minus 7, because 3 times minus 7 gives negative 21. The inside bit here, as I say, I can write that over 1, and now I'm going to do the top multiplied by the top, and the bottom multiplied by the bottom. So the top becomes x plus 4 multiplied by 2x plus 3, and the bottom of it becomes 2x squared minus 6x minus 56. So this bottom part here, quite clearly, is a quadratic expression. Now, before factorizing the quadratic and just jumping into it, just check the coefficients, just check the numbers. I've got 2, 6, and negative 56, which are all even values. So before we factorize into 2 brackets, be thinking we could factorize out this 2 before we do anything else more complicated. That's what we're going to do here. So just factorize out the 2 from this whole quadratic, and then the inner quadratic, just half all these numbers at the front, we get 2 lots of x squared minus 3x minus 28. Now this quadratic here, we can factorize using the standard thing you've seen, probably going back to year 8 or year 9. So the standard rule here is we need to find a pair of values which multiply together to give negative 28. When we add these 2 values together, we end up with negative 3. After a bit of thinking, pause the video now if you need to do this yourself, you should find the 2 values at work are positive 4 and negative 7. We can therefore factorize this into x plus 4 and x minus 7. A common theme when solving questions which are algebraic fractions is to also look for cancelling once we've factorized. So it's often a case of factorizing and cancelling. So I've got an x plus 4 bracket at the top and an x plus 4 bracket on the bottom, so I can cancel top and bottom to get rid of the x plus 4. That'll then give us this expression here. So I've got this fraction here, which is still the same thing, 14 over 3 lots of x minus 7. And here, I've just got 2x plus 3. I've not cancelled that 2, so remember to include that, plus 2 lots of x minus 7. We're actually almost done here. Now again, just ignore the algebra for a second and remember what we're actually doing. In simple terms, this is just a fraction, although it looks horrible, and I'm adding another fraction. Go back to year 7. How do we add fractions together? What do we need to check for? We need a common denominator. The bottom numbers need to be the same. They're almost the same because this is 3 lots of x minus 7 and 2 lots of the same thing. But of course, 3 isn't the same as 2. So what could I get the 3 and the 2 both to become by multiplying by some value? I'm hoping you can see I can get them both to become 6. I could multiply top and bottom of this one by 2 and the top and bottom of this fraction by 3. And that's exactly what we're going to do. I'll then end up with 6 lots of x minus 7 on the bottom of both fractions, and after that step we can then combine the tops together. So the first fraction will become 28 over 6 lots of x minus 7. Tripling everything on the top here, that's going to become 6x, 3 times 3 is 9, and triple the bottom, I get 6 lots of x minus 7. Because the bottom of the fractions are now the same, I can merge them. I can combine them into one. So the next step I'm going to get is 6x plus 28 plus 9. But 28 plus 9, of course, is 37. I've got it all into a single fraction, so it's tempting to think you've done the question in its entirety and move on. But just stop for a second. You're about to lose the last mark. What it says here is to give it in this form here. There's no brackets in the form it's asking for. I've got brackets here. So what I need to do as a final step is to expand out this denominator. 6 lots of x minus 7 is the same as 6x minus 42. This is now in the form we required. A is 6, B is 37. Not that we need to say this as such. C also happens to be 6. It doesn't say A and C have to be the same, so that's allowed. And D is negative 42. So that's question 20 complete. And finally, question 21. You've made it, the very last question of the paper. It's a Venn diagram question and probability, so let's get straight to it. So Vicky has a collection of medals. Good for her. And this Venn diagram I've put to the right-hand side. It shows information about the number of medals in her collection. The curly E, as ever, represents everything, in this case, all the medals. So everything in the rectangle represents every single medal in her collection. The capital A, whatever's in this circle here with the A on it, represents all of the English medals. Everything in this, not really a circle, I should say ellipse, which is the fancy name for a flattened circle. Everything in this region B is all of the gold medals, and on the outside is a medal, but those which are neither gold or English ones. But there's still medals in her collection because that 34 is still inside the rectangle with the curly E in it. And I'll just mention the bit in the middle, because this X is included in the A region and the B region. The X therefore represents those medals which are both gold and English ones. So in other words, it must be where she's got a gold at English, I would imagine. Anyway, she's going to take at random a medal from her collection. And the wording here says, given that the medal is gold, the probability that the medal is English is 2/11. Now this wording, I'll just focus in on this in a second. So if I colour in the region A in a blue outline and region B in a green outline to just highlight the difference, like so, and given that the medal is gold, all that means is we just focus in on the medals that are gold. Another way of saying this would be, I'm telling you for 100% certainty that the medal we're talking about is a gold one. So given that the medal is gold is another way of saying ignore everything else apart from the gold. So we're going to focus on the gold, which I'm going to highlight again in a different colour. So I'm going to highlight it in yellow to emphasise that we're just focusing in on the region of them which are gold. So we can see the gold ones are represented by the X and the 5x minus 3. So the total gold medals are X plus 5x, 6x, take away 3. So the probability that the medal is English and gold is 2/11. Well, the only bit of this region which could be an English medal is this bit here, which is the X. So the English ones, out of all the gold, is X out of the total of 6x minus 3. So as a fraction, X over 6x minus 3, that's a fraction of them that are gold, must be one and the same as 2/11. Just as the same thing as the chance of rolling a 6 on a dice is 1/6, because one side out of those 6 in total is a 6. So we can write this down as an equation. So the medal being English is 2/11, like I've said, and the English and gold is Vx, and the gold ones are Vx and the 5x minus 3. So as a fractional equation, we've got x out of 6x minus 3. The gold ones the English ones out of all the gold must be the same as 2/11ths. We can solve this in a few different ways. I'm just going to go for cross multiplication because I find it easiest. All this means is each opposite corner multiplied is equal to the other opposite corner multiplied together. So x multiplied by 11, 11x, is equal to 2 lots of 6x minus 3. In other words, 11x equals 12x minus 6. I've expanded this in one go. I could have wrote it as 2 brackets 6x minus 3 and then expanded, but I've expanded it in one step. 2 times 6x is 12x, and 2 times minus 3 is minus 6. I'm now going to get all the x's onto the same side of the equation by taking away 11x from both sides. So 11x take 11x becomes 0. On the right-hand side will just become x take away 6, because 12x take away 11 of them will just leave us with 1x. I want to isolate the x on its own. So to get rid of negative 6, I do the opposite and add 6 to both sides. So x minus 6 plus 6 just leaves us with the x, and 0 plus 6 equals x. In other words, x must equal 6. So we've solved for 6, and the trouble is often in secondary school you're conditioned to solve equations to find x. And you do that so much, that's often the last step. And it's tempting to think you've therefore done the last thing and you're finished. But actually, no. What we need to do here is to actually work out the number of medals in Vicky's collection in total. All we've done so far with finding x is 6. We've only found out the number of medals which are English and gold. The total number of medals in her collection is everything, not just this x. So if I deselect the gold for a second, get rid of the yellow highlight, and if I put a red box around every expression, which represents all of the medals in total, we can see, hopefully, we need to actually sum together these 4 different expressions, and that'll tell us the total number of medals. In other words, the total number of medals is this 7x minus 11 plus the x plus this 5x minus 3 and plus 34. We could either simplify this first and then sub in the fact we know x is 6, or we can sub in right away that x is 6 and then simplify down this calculation on our calculators, because after all, it is a calculator paper. What I tend to realise people want to do is to get rid of the algebra as quickly as possible and just sub in x is 6 straight away. So if I do this way, either way would have worked. The total number of medals is 7 lots of 6 minus 11 plus x, which is 6, plus 5 lots of 6 minus 3 plus 34. You could type that into your calculator straight away, or if you want to just do it slightly longer-windedly, 7 times 6 is 42, 5 times 6 is 30. Put that into your calculator, see what you get, and hopefully you'll agree that the total number of medals must therefore be 98. And we've finished question 21, therefore the whole paper, so you can breathe a sigh of relief, put your pen down, and relax for a second. So I hope you found that question okay to an extent, and hopefully what you've listened to in this recording, whether it be a few questions, just for one question, or lots of it, I do honestly hope you found it useful. Do feel free to leave me a comment in the comment section, either way around. I'll try to get back to you. And thank you very much for tuning in. It is always appreciated. And I'll finish with saying, as ever, the best of luck with your actual GCSE exams. So for myself, Mr. Bailey, it's goodbye for now. Take care.